This is Mrs. O'Neill for AP Chemistry, Chapter 6, Section 2, Quantized Energy and Photons. First, you should have watched the introductory lesson on light and matter. Here are my notes. So matter is what we're made of, but we need light in order to see it. So he went through how light are photons, and he talked about that equation E equals Planck's constant times frequency. And then he went through matter and how molecules can either be infrared, ultraviolet, or in solutions. And he talked about absorbing to find out the concentration. So he talked about light is a wave and a particle, and it's a particle because it's quantized. And he showed you this electromagnetic spectrum from radio waves all the way to gamma rays. And he talked about how we have low frequency here, but we have high frequency here. So we have long wavelength here and short wavelength here. So we talked about how a violin is very different than a piano because a violin can play any note, because it's just talking about how your fingers move across that string. However, in a piano is quantized. You hit specific notes for a specific quantity of sound. So we can measure that energy using Planck's equation, E equals hv, and that will be on your reference sheet. And it just is going to get us to understand how to measure the energy that these electrons are going from the, remember that electrons in a ground state go to an excited state, and when it goes back down to that ground state, it gives us that light energy. So again, most of the energy that we see, though, is in the visible part of the electromagnetic spectrum. So we can measure the amount of energy because we're going to use Planck's constant times the frequency. And we want to remember low to high energy. So we have low energy with long wavelength and low frequency, but we have high energy in the area where there's short wavelength but high frequency. So we need to keep that in mind. So you can use a spectroscope to do this, and he talked about how a spectroscope is used. And then he talked about a spectrometer, just a different kind of spectroscope, just more sophisticated. Talked about what infrared really gives us, the information that an infrared system would give us. And that talked about how to look at bonds and how they're related to each other. And we'll talk about that in more detail as we go through the course. And he also talked about how electronic structure really deals with the UV or the visible light and how the electrons are moving. Again, going back to the amount of energy in a specific electron. So then he talked about this Beer-Lambert Law and about how molecules are absorbing some of that light that is being shined through that sample of solution. Then he used that PhET simulation. Again, I suggest you go and play a little around with it. We'll try to do a lab. But as increased concentration, there'll be less light that goes through the solution because more of the light is actually being absorbed because there are more particles. So the more particles that you have, the more that the light is going to be absorbed. And of course, that means that you have more concentrated solution. So then he graphed it, and then obviously using a graph, you can kind of go the other way. If you have a graph of your solution and concentration or your absorbance, then you can find out what the concentration of a solution is. So now back to your packet of notes. The objective for this section is to recognize that electromagnetic radiation also have particle-like properties, and we call them in terms of photons. So how does electromagnetic radiation and atoms interact with each other? 3 ways: black body, photoelectric effect, and emission spectrum. So again, I suggest you pause the video, fill in the blanks, and then play to hear my words. So emission of light from hot objects is what we call black body. So the objects studied appear black before actually they're heating up, and that's why it's called black body. Where the photoelectro effect is the emissions of these electrons from the metal, which light shines. So like that's why your metallic surfaces, we call them shiny, because when light reflects off of them, it gives it that like shimmering glow. And then of course you have that emission spectrum, where the emission of light is from gas atoms. And we're going to talk about that more in detail as well as we go through the course. So hot objects and the quantization of energy. So solids are being heated. They're going to emit irradiation in the form of light. So think about your stove and how it emits red light, or think about a light bulb that emits white light. Okay, so the wavelength of this radiation is going to depend also on temperature. So we always kind of say red is for hot things and white, red hot is colder than white hot. So kind of is weird to think about that, but your red hot stove is kind of cooler than your white hot light bulb. So physics studied the relationship then between temperature and the intensity and wavelength of this radiation, and that was in the late 1800s. So in the 1900s, though, matter and energy were seen as different things from each other. Matter was particles and energy was waves, like frequency. But this Max Planck found that the cooling of hot objects couldn't be explained by viewing energy as a wave. So there's Mr. Max Planck himself. So energy is quantized, okay? And that's where this relationship between energy and his constant and the frequency plays a part in it. So this Planck's constant is on your reference sheet, and you need to use that. So he called this the packets of quantum. So remember quantum theory? We talked about that, and we're also going to talk about the 4 quantum numbers soon. So remember that if we look at a light bulb, light sometimes behaves as a wave and sometimes it behaves as a particle. So hot objects, like a light bulb, give out this light as waves and as particles. So calculate the energy of one quantum of electromagnetic radiation whose frequency is 5 times 10 to the negative third per second. So figure that out using that equation. And then can this radiation produce a burst of energy? E equals 5 times 10 to the negative 36 joules. Why or why not? Well, if you plug and chug, right, using HV, you will see that it's 3 times 10 to the negative 36. So no, it cannot produce that amount of energy. It can only produce 3 times 10 to the negative 36 instead of 5. Okay, so those are kinds of questions or problems that you'll see. So this photoelectro effect in photons, Einstein actually said electromagnetic radiation is quantized in particles called these photons. So again, remember we talked about, or in Chem 1, you should have done that flame test lab where energy, we excite the electrons using energy by heating them up in a flame test, and those electrons go from a ground state to an excited state, and when they jump back down to their ground state, they give us this energy of light, and we're going to call that the photon energy of light. So there's Mr. Albert Einstein himself. So again, give it one more thought. Which has more energy, a photon of infrared light or a photon of ultraviolet? Well, how would we see that, or how would we know that? Well, ultraviolet, because that region has higher frequency, therefore greater energy. So again, if we look at the electromagnetic radiation, we'll see that going from gamma to X-rays to ultra to visible to infrared to microwaves to radio. So I like to actually remember it the opposite way, all the L's on the left. So here's low energy, low frequency, long wavelength. So I like to say L, 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 L. Low left, on the left side, there's low energy, there's low frequency, and then there's long wavelength. Okay, so it's up to you how you want to remember that. And then red for like radio. So I kind of think about the left-hand side, and that's where your visible light, red to purple, if you want to think about the rainbow. Okay, so what is the unit on the spectrum? nanometers, NM for nanometers. So how do we convert this to meters? Well, do an example. Convert 650 nanometers to meters. Again, pause, try to do it on your own, and then play to hear the answer or see the answer. Okay, so nanometers is 9 zeros. We want to remember that. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros for nanometers. Okay, see you in class.